For chapter 15, we're going to cover how the brain thinks. We're going to review the nature of thought, cognition, and the association cortex. What are some of the fields that are involved in expanding the frontiers of cognitive neuroscience? We're also going to talk about cerebral asymmetry in thinking. We're going to go over gender and handedness variations in cognitive organization. And then finally, we're going to be reviewing intelligence and consciousness. So beginning with the nature of thought, when we think of thought, we tend to think really sort of metaphysically, similar to the I think, therefore I am. But when we delve into the definition of a thought on a psychological or neural level, thought is actually a psychological construct. Specifically, it is an idea resulting from a set of impressions that some mental ability exists as an entity. Examples include memory, language, and emotion. It's difficult to localize constructs in the brain, so we don't really have a specific place for memory. We don't really have a specific place for emotion. We don't really have a very specific place for language. While there are key processing regions in the brain involved in language, it's not just one thing. In order for you to process and speak language, it's a host of regions that are involved in that construct. Similarly, there's no one place where memories are stored, or there's no one place where emotions are processed. There are a couple of regions that are essential for forming new memories, primarily the hippocampus, and the amygdala is very important for processing psychologically relevant stimuli, which tends to be emotional stimuli. But there is no region that just processes emotion, and there's no particular place where you can go and access stored memories. This diffuse representation makes it really difficult to localize constructs in the brain. Cognition is actually an act or process of knowing or coming to know. So in psychology, cognition is used to refer to the process of thought. So we have explicit memories, things that we tend to think about consciously that we recall. This tends to be what we think about when we think about cognition, and we will think about particular events, process information, come to realize particular behaviors or events have meaning. So this is generally what we think about, but it's not bound only to explicit or conscious information. You can also have a process of knowing or coming to know at the unconscious or implicit level, which would really refer to the fact that your body is also processing things and your brain is processing things that you're not necessarily aware of. So when you're learning to ride a bike, then there are certain things that your body does, processes that it engages that you are not aware of, but your body is still engaging in that process of coming to know something or how to do something. So cognition does not just refer to things that you are consciously aware of. One of the key characteristics of human thought is language. Language gives humans a fundamental edge in thinking. Language provides the brain with a way to categorize information. This is really important. So when you see something, you see a dog, then you can think about the various ways that it can be categorized. It's categorized as a pet, an animal, a mammal. If you see a cow, then you would categorize the cow as an animal, bovine, particular type of animal. You might categorize a cow as something that could be eaten and made into meat, and we wouldn't necessarily think that way about dogs, although in some cultures that would actually be different. So language provides this fundamental way to categorize information so that we know how to think about and organize what we are encountering in the world. Language also provides a means of organizing time. Monday at 3 p.m. So this could be a future time, this can be a past time, and humans have a fundamental ability above and beyond most animals to organize time. Some animals have the ability to look in terms of the past and maybe to short expectations with regards to the future. Animals will store food, for example, for a later time, but humans have a much more complex way of organizing time so that we can pursue complicated long-term goals. Language also has syntax, ways in which words are put together to form phrases, clauses, or sentences. This is proposed to be a unique characteristic of human language, and it helps humans communicate and make sense with regards to what someone is saying so that the correct meaning is derived. Syntax also allows humans to have a language that moves beyond the concrete world of the here and now. There's certain elements of syntax that denote future tense, past tense, and provide us with this ability to communicate across time and space. So a fundamental question is, how is it that thoughts actually arise in the brain? We all have thoughts. We think about all sorts of things. The people that we love, the people that we don't like, our hopes, our dreams, the things that we're afraid of. And what is interesting is that at a very basic level, neurons, the firing or non-firing of neurons, is the foundation of thought and cognitive processes in the brain. So thoughts actually have a very physical representation. In order for you to have a thought, there must be some physical change, some physical instance that is occurring to correspond to that thought. So neurons must be either firing or not firing, or you can have a change of the rate of firing, which would correspond to something else. You could have more firing in one area and less in another. The neurons that would fire or not fire to comprise a thought are known as cell assemblies. So multiple neurons converge to form cell assemblies to represent complex thought. Cell assemblies provide the basis for cognition. You have different ensembles that come together, much like words and language, to produce coherent thoughts. So also, just like you would have different instruments, that one instrument would just provide one tone, one musical quality, but when you put multiple instruments together, then you have way more than the sum of its parts, and you can have a much more complex communication of musical harmony. So cell assemblies basically correspond to the neurons that are involved in representing a particular piece of information. So if you were to think of a little dog, and you have in your mind a little dog, then there's all sorts of neurons that would be firing. They would be neurons involved with the auditory information associated with a small dog, the type of way that they fire, visual information, what a small dog would look like, also what a small dog would feel like. You might have particular memories and associations if you have a small dog or if you've owned one in the past. People also tend to differ in how representative they think little dogs are of dogs more generally. So I, for example, am more of a big dog person, and some people are more of a small dog person. Primarily my experiences with dogs have been bigger dogs. And I also have cats. And so I happen to have large cats. So when I see really small dogs, they don't seem very much like dogs to me if they are smaller than my cats, because there's an element of size that can be associated with the stereotypical dog. So all of those different features that I mentioned, the sound, the touch, the visual aspects, personal episodic memories and experiences, there are neurons that are firing when you see or even think about that information. So that particular ensemble of neurons, that particular collection, that would be a cell assembly. And so you would have a distributed collection of neurons across the brain that, when activated, would mean that a thought, a particular thought is currently active in your brain right now. And so that is basically a cell assembly. And that is also the neural foundation of thinking, that when we are engaging in the act of thinking about information, our neurons are firing in a particular pattern that corresponds with the particular information that we're thinking about. Building on this, neurons are the only elements in the brain that combine evidence and make decisions. So when we have various thoughts floating around in our mind, we're trying to focus on one particular thought over another, then neurons are firing that correspond with those thoughts. And the thoughts that receive the majority of our attention, of our cognitive resources, they are going to most likely be more active, or those particular cell assemblies are going to be more active to represent the maintenance of that particular information. And if we're trying to actually make decisions from what we would like for dinner, or what we would want for a snack, how much money we want to spend, typically when we do that, we have multiple pieces of information or thoughts that we're choosing between. And when we are in the act of choosing, some particular possibilities are more active or less active than others. So we could be in particular mood for one type of snack or one type of dinner. And so that representation will actually be more active. The neurons will be firing more often. The neurons will be firing stronger. And when we make decisions, we might be looking for that type of increased signal. This is basically known as signal detection theory. And that's one of the things that our brain does, is it looks for the presence of signal versus non-signal. So when we make choices where our neurons are looking for firing from other neurons or non-firing from other neurons, something being on or something being off. And that difference will enable information from multiple regions of the brain to be assimilated so that neurons can combine evidence and make decisions. So now that you have a basic idea of the role of neurons in thought and how you have cell assemblies that can be distributed throughout the brain, the next thing we want to understand a little bit more about is where some of these cell assemblies would be. So we have particular regions of the brain that are involved in processing sensory information: the primary visual cortex, the primary auditory cortex, the primary somatosensory cortex, the primary motor cortex. So these, at a fundamental level, process incoming sensory stimuli or direct movement. But most of the things that we do combine sensory information so that what we're processing is actually multimodal. And where this information gets combined is in association cortices, or association cortex. Association cortex is the neocortex outside the primary sensory and motor cortices that functions to produce cognitions. So it is in the association cortex that you would have cell assemblies that would combine multimodal information from different sensories. The association cortex receives information that is more highly processed than information received by the primary cortices. So in the primary cortex, for example, you might process basic visual information regarding shading, color, light intensity, and then you move out into the secondary visual processing, or the extrastriate cortex, and you will start to combine that information so that you will have more complex visual features. When you move into the association cortex, then you might be combining visual information and auditory information so that you have more complex representations still. You might be combining visual and auditory information so that you have even more complex thoughts and cognitions. The temporal association region is one of the primary association cortex. It produces cognition related to visual and auditory processing. The parietal cortex, this is related to somatosensory processing and movement control. So this is particularly important for attention and spatial processing. And then you have the frontal cortex. This coordinates information from the parietal and temporal association regions with information coming from subcortical regions, such as the amygdala. So you have, I guess, three primary association cortices: the temporal association regions, the parietal association regions, and the frontal cortex regions. The biggest association area of all is your frontal lobes. Your frontal lobes, aside from the primary motor cortex, is a very large region of the brain that doesn't actually engage in any primary sensory processing. So it really just organizes and associates lots of information. So the frontal cortex is basically a very, very large association cortex. So now that we have this information that's coming in from the multiple sensory regions, how is it that we actually bind this information together? So this is known as a binding problem. How does the brain tie varied sensory and motor events together into a unified perception or behavior? So we have our unified perception of a dog. Well, again, that contains all sorts of sensory and motor information that would be processed in the primary sensory regions of the brain. So how does this come together? Regions of the association cortex are multimodal. The neurons in association cortex respond to information from more than one sensory modality. So basically what this means is that if you have a representation of a dog, and this representation of a dog would correspond to a cell assembly in one of your association cortices. And if you were to think about what are the things that activate or make you think about a dog with this representation, you could hear the sound the dog makes. And if you hear a dog barking, then that will call to mind a dog. It could be a particular type of dog. It could be your own. You could see a picture of a dog. You could see a dog sitting across from you. So that would also activate your representation of a dog. And you could also feel a dog in terms of pet it. So you have these three different types of senses, and even if you were to hear or if you were to see the dog or a picture of a dog, then both of the sensory information would activate this multimodal representation. And most more complex thinking uses multimodal neurons. So spatial cognition, attention planning, all use multimodal neurons in the association cortex because it's very, very important to combine information from across the senses so that you can recognize information that you're seeing in the environment quickly and be able to respond to it quickly.